Hello everyone. So today we are going to discuss the chapter organic compounds containing oxygen. First part we'll be discussing today. So in this part we'll essentially be discussing about the chapter alcohols, phenols, and ethers. Okay. So alcohols and phenols are formed when a hydrogen atom in a hydrocarbon, aliphatic and aromatic, respectively is replaced by OH group. So what do you say? Aliphatic or aromatic hydrocarbon. We'll note this RH or aromatic. Hydrocarbon we represent by ARH. We replace the hydrogen by what? OH group. To replace this, we get aliphatic. We get alcohols and phenols. It is attached to an aromatic ring. We call it a phenol. Alcohol contains one or more hydroxyl groups directly attached to a carbon atom of an aliphatic system, while a phenol contains OH group directly attached to a carbon atom of an aromatic system. In alcohol, the OH group is attached to an aliphatic carbon system. In aromatic, it is attached to a aromatic ring like benzene. The substitution of a hydrogen atom in a hydrocarbon by an alkoxy or aryl oxidate. So, in aliphatic or aromatic hydrocarbon, when we replace a hydrogen by an alkoxy or aryl oxy group with a person by ROA, when we replace this, we get what? We get ethers. ROR when the hydrogen is replaced by alkoxy or aryl oxy group, we get ethers. So we have given an example here, dimethyl ether. So here we replace the hydrogen atom of what methane with OCH3 group. So we got dimethyl ether. Now classification of alcohols, monodyne, tri or polyhydric alcohols. Alcohols and phenols may be classified as monodyne, tri or polyhydric compounds depending on whether they contain 1, 2, 3 or many hydroxyl groups respectively in their structures. So depending on the number of OH group, we may classify alcohols into mono, di or trihydric. So here we have an example of ethanol, which is it's a monohydric alcohol. And here we have ethylene glycol, which is a dihydric alcohol. And here it's an example of trihydric alcohol. Monohydric alcohols may be further classified according to the hybridization of the carbon atom to which the hydroxyl group is attached. So depending upon whether the OH group is attached to an sp3 hybridized carbon or sp2 hybridized carbon, we can again classify monohydric alcohols. Let's see how it is classified. First, compounds containing sp3 carbon sp3 OH bond. So when OH group is attached to sp3 hybridized carbon. In this class of alcohols, the OH group is attached to an sp3 hybridized carbon atom of an alkyl group. They are further classified as primary, secondary, and tertiary alcohols. So you can see here the carbon is sp3 hybridized. To that, one OH group is attached, and this sp3 hybridized carbon is only attached to another carbon atom. So it's called a primary alcohol. So if the OH group is attached to sp3 hybridized carbon, which is attached to other two carbon atoms, it is called secondary alcohol. I mean, OH group is attached to a sp3 hybridized carbon, which is attached to other three carbons. We call it as a tertiary alcohol. What is allylic alcohols? In these alcohols, the OH group is attached to a sp3 hybridized carbon adjacent to the carbon-carbon double bond, that is to an allylic carbon. So here, what our OH group is attached to sp3 hybridized carbon only, but that sp3 hybridized carbon is attached to what? An sp2 hybridized carbon. So here we can have an example here. Our OH group is attached to sp3 hybridized carbon, but that carbon is attached to what? Attached to an sp2 hybridized carbon. Here also same. Here is sp2 hybridized carbon is here, and to that our sp3 hybridized carbon to which OH group is attached. So next, benzylic alcohol. Here also what? Here also OH group is attached to sp3 hybridized carbon, but that carbon is attached to the benzene ring. Here we can have the example of a primary, secondary, and tertiary benzylic alcohol. Okay, going on. Compounds containing carbon sp2 OH bond. So here what? Here the OH group is attached on sp2 hybridized carbon. So these alcohols contain OH group bonded to a carbon-carbon double bond, that is to vinylic carbon to an or to an aryl carbon. These alcohols are also known as vinylic alcohols. So here what? Here it is. It's an example. CH2 double bond CH. Here the OH group is attached to sp2 hybridized carbon directly. So it is a vinylic alcohol. Or the OH group is directly attached to an aromatic ring, like phenol. So we know in phenol carbons are sp2 hybridized. So here our OH is being directly attached to sp2 hybridized carbon. So these are also example of vinylic alcohols. Now phenols, mono, di, and trihydral phenols. So according to the number of OH group directly attached to the aromatic ring, we classify phenols again into mono, di, and trihydral phenols. So here we have an example. Phenol is a monohydric alcohol. So here an orthotoluene, which is also a monohydric alcohol. This is a dihydric alcohol because two OH group are directly attached to the ring. This is an example of a trihydric alcohol. Ethers. Ethers are classified as single or symmetrical if the alkyl or aryl group attached to the oxygen atom are the same, and mixed or unsymmetrical if the two groups are different. So we will discuss with this with example. So we'll take two ethers here, CH3 or CH3 and C2H5 CH3. So when we look at this first compound here, we can see that on either side of the oxygen atom we have the same alkyl group, which is methyl. We name it as dimethyl ether. So common name of this compound. So when on either side the same group comes, we call it as what? We call it as simple or symmetric. Coming to the second compound, you can see on either side what different groups are coming. On one side we have the methyl group, the other side we have the ethyl group. We name it as what? Ethyl ether. So since the groups on either side of the oxygen atom are different, this type of ethers are called unsymmetrical or mixed ethers. Okay. Now we'll see nomenclature of these compounds. First, alcohols. The common name of an alcohol is derived from the common name of the alkyl group and adding the word alcohol to it. So for deriving common names of alcohol, we simply substitute the add the term alcohol to the common name of the alkyl group from which the alcohol is prepared. So here we have CH3OH. CH3 group, as we always know, is known as methyl group. So for methyl group, we are adding the term alcohol to the end of it. So the common name of this compound is methyl alcohol. According to the IUPAC system, the name of an alcohol is derived from the name of the alkane from which the alcohol is derived by substituting E of alkane with the suffix ol. So what in IUPAC system first? Let's consider the same example of CH3OH. So in IUPAC system, we consider alcohols as the what we think of it as what the hydroxyl group is replacing the hydrogen from the alkane. So here the alkane will be what? CH4. And OH group is substituting one hydrogen. So we know this name of CH4 group is methane. And we think of it as what we think as the substitution product. We are substituting one hydrogen atom with OH group. So we remove the E from the end of the name and add a suffix ol to it. So we get what? We get methanol, which is derived from CH4. So the alcohol will be CH3OH. That will be the name of this compound. The number of OH groups is indicated by adding the multiplicative prefix di, tri, etc. before all. So there are more than one hydroxy group present. We add the prefix what? Di, tri to indicate the number of OH groups present in the compound. The positions of OH groups are indicated by appropriate locants. So we also denote the position of the OH group in the compound by assigning number to the carbon chain and showing it in the name. Cyclic alcohols are named using the prefix cyclo and considering the OH group attached to C1. So for cyclo compounds, for example, we'll take a hexagonal chain here and it's attached OH group. So here, when we number the carbon, we number taking the OH bonded carbon as the first carbon. So here 1, 2, 3, 4, 5, 6. So the name will be cyclo. We will add the prefix cyclo. Cyclo hexanol. Hexanol. So we'll see the names of some compounds here. First, CH3OH. Simply called methyl alcohol, IUPAC methanol. We saw that. Now coming to this, we have here the isopropyl group here. Isopropyl group, we are attaching the OH group. So the common name will be simply isopropyl alcohol. For IUP system, it will be OH group will be attached to the second carbon. The name will be propanol. So the N-butyl group, N-butyl alcohol, will be the secondary butyl group. It will be the isobutyl group. It will be the tertiary butyl group. So in such places, we use the same terms for denoting the common name. IUPAC name will be done according to the numbering the carbon chain and assigning the position of the OH group. Now for polyhydric alcohol, for example, here we have ethylene glycol. Here it's known as ethylene glycol. So when we assign the position or the carbon chain will be 2 carbon long. So the name will be ethane 1,2-diol. So here we have glycerol molecule here. When we number, it will be each hydroxy group is attached to each carbon of the glycerol molecule. It will be propane 1,2,3-triol. So yeah, some examples of cyclic compounds also given here. Now moving on to phenols. Nomenclature of phenols. The simplest hydroxy derivative of benzene is phenol. So simplest hydroxy derivative of benzene is phenol because we are already attaching one OH group to the benzene type. Its common name and also an accepted IUPAC. So benzene is an accepted. No, sorry, phenol is an accepted IUPAC name. The structure of the phenol involves a benzene ring in the substituted compound with term ortho, meta, and para are often the common name. So for assigning common names, we also use the term ortho for 1,2-disubstituted product, meta for 1,3-disubstituted, and para for the 1,4-disubstituted product. We'll see some common names and IUPAC. First, phenol. It's an accepted common name also, as well as IUPAC. Now here, so here we assign first position to the OH bounded carbon, second to the methyl group. Here also 1, 2, 3, 1, 2, 3, 4. So for assigning names, we have here what? IUPAC 2 methyl phenol, 3 methyl phenol, and 4 methyl phenol. And when OH and CH3 groups are both attached to the benzene ring, we name the compound as cresol. So depending upon the position, we can name it as what? Orthocresol, metacresol, and paracresol. Such are the common names of the compounds. Now, derivatives of benzene are known as 1, 2, 1, 3, and 1, 4 benzene diols. So if dihydroxy derivatives are present, we can use the term benzene because benzene is an accepted IUPAC name. So we can use benzene. I'm sorry. So dihydroxy derivatives of benzene are known as 1, 2, 1, 3, and 1, 4. So according to the position, we can use the IUPAC name. Now, here we have some common names which we have to know for these compounds. So 1,2 disubstituted phenols. It is known as what? Catechol. It is meta-substituted we have to call it as isocinol. Para-substituted we have to call it as hydroquinone or hydroquinol. So these common names are also very important. Now coming to ethers. Common names of ethers are derived from the name of the alkyl or aryl group written as separate words in alphabetical order and adding the word ether at the end. So how will we assign common names? Let's consider CH3 OCH2. So C2H5. Okay. So we have a methyl group and methyl group. So according to the alphabetical order, which word should come first, ethyl or methyl? So E comes before M. So we will, when we write the name, we write as ethyl, then methyl, and we add the term ether at the end. This is how we write common names for ethers. Ethyl, methyl, ether. If both the alkyl groups are the same, the prefix di is added before the alkyl group. So on either side of the oxygen atom, we have the same group. For example, CH3 or CH3 or C2H5 or C2H5. So we simply add di before the name. So here the name will be dimethyl ether. And here we have dimethyl ether. According to the IUPAC system of nomenclature, ethers are regarded as hydrocarbon derivatives in which a hydrogen atom is replaced by an alkoxy or aryl oxy group, where R and A are represent alkyl and aryl groups respectively. The larger R group is chosen as the parent hydrocarbon. So we see the names here. So we have CH3 or CH3. We already named this compound for common name is dimethyl ether. So here we consider the alkoxy group as substitute for hydrogen atom. So when we name it, we add the name oxy with the name before as prefix of the parent carbon chain. For example, here we take one of the carbon CH3 group as a parent carbon chain and other as the substituent. So the name will be methoxy methane. Here it will be ethoxy ethane. So here it will be CH2 CH. Here the propane carbon chain is the parent carbon atom. So this will be the substituent. It will be what? Ethoxy propane. So we name the compounds in this manner. Okay, now moving on. structures of functional groups. In alcohols, the oxygen of the OH group is attached to carbon by sigma bond formed by the overlap and sp3 hybridized orbital of carbon with the sp3 hybridized orbital of oxygen. So what in alcohol? For formation of alcohol or oxygen OH, when OH is bonded to carbon atom, what is happening there? The sp3 hybridized carbon is overlapping its orbitals with sp3 hybridized orbital of oxygen. The bond angle in alcohol is slightly less than tetrahedral angle. It is due to the repulsion between the unshared electron pairs of oxygen. In phenol, the OH group is attached to sp2 hybridized carbon of an aromatic. So, when OH group is attached to an sp3 hybridized carbon, the bond angle should be theoretically what? 109.5 degree tetrahedral angle. But it's observed that the bond angle is slightly lesser than that because of what? Because of the lone pair present on the oxygen atom, the bond angle is slightly less than that. You know, phenol OH group is attached to the sp2 hybridized carbon of atom. The carbon oxygen bond length in phenol is slightly less than that in methanol. So in phenol, the what you observe is that this bond length is slightly lesser than what? Than alcohols. Why? Because of resonance happening there. This bond has what? This bond has partial double bond character. And not only that, in this compound, what? This compound, the oxygen atom is attached to an sp2 hybridized carbon. And we know that as the S character of the atom increases, the electronegativity also increases. So this carbon will have more electronegativity than normal alcohol. So higher electronegativity. That's also another reason for the shorter bond length. The carbon oxygen bond. This is due to partial double bond character on account of the conjugation of unshared electron pair within the aromatic ring and sp2 hybridized state of carbon to which oxygen is attached. In either the 4 electron pair, that is the 2 bond pairs and 2 lone pairs of electrons on oxygen are arranged approximately in a tetrahedral arrangement. The bond angle is slightly greater than the tetrahedral angle due to repulsive interaction between the two bulky groups. So in ethers, we can see how do we write R O R. We already know that oxygen has what 4 electrons for 2 lone pair there. So this also theoretically the angle should be what 109.5 degree should be the angle bond angle, but we have seen that this angle is slightly higher than this because of what? Because of this repulsion between the bulky alkyl group, the bond angle is slightly greater. The CO bond length is almost the same as an alcohol. So carbon oxygen bond length is almost the same as in alcohol. So we can compare the bond angle and bond length of an alcohol, phenol, and neither. So in alcohol, we see as expected the bond angle is less than 109.5. For a phenol, almost the same. For neither it is greater than 109.5 because of the repulsion of the bulky alkyl group present. And also, you should note that the bond length of carbon oxygen in phenol is lower than that is observed with the alcohol and ether. So we have already stated the reasons for the shorter bond length because of the partial double bond character and higher electronegativity of the sp2 hybridized carbon. Now alcohol, we'll see the preparation of alcohols. From alkenes by acid catalyzed hydration, alkenes react with water in the presence of acid as catalyst to form alcohol. So they react with water in presence of an acid to what? the double bond is broken and an OH group is introduced. So how do we decide where the OH group is gonna enter? So we have seen that in alkene, two carbons, the double bond is shared between two carbons. So how do we decide which carbon gets the OH group? This according to Markovnikov's rule. What does it say? The highly substituted product, which will be, so we have an example here. This example, the OH group can go to both the first carbon and the second carbon. And we see it goes to the second carbon because that is the more substituted product. Now we see the mechanism of this addition. So this occurs by three steps. What is the first step? Protonation of alkene to form carbocation by electrophilic attack of H3O plus. So water combines with H plus to form what? H3O plus or hydronium ion. This hydronium ion goes and attacks the alkene first. What the double bond is shifted. So one carbon will get slight positive charge and the other carbon will get negative charge. And the hydronium ion has a positive charge. So this bond gets shifted towards the oxygen and H plus is created. So this H plus comes and attacks the negatively charged carbon. And therefore we'll get what? We'll get a carbocation in this step. Nucleophilic attack, what is the second step there? Second step is nucleophilic attack of water on carbocation. So the water molecule goes and binds with the carbocation because oxygen has a lone pair here. So by donating the lone pair, oxygen gets a slight positive charge here. Then what's the third step? Deprotonation to form alcohol. So here what happens here? To compensate for the positive charge, this bond gets shifted towards oxygen. And so what? And so the H plus is created here. This H plus goes and binds with the H2O to form what? Again, a hydronium ion. And we get an alcohol as a product here. So the H3O plus that is used in the beginning of the reaction is again regenerated at the end. Now second method of preparation is by hydroboration oxidation. Diborane or B28 reacts with what? Reacts with alkenes to give trialkyl boranes as addition product. So here the steps are given. Reacts with diborane to form what? Form alcohol. But what to note here? See, here we see the position of OH group here. OH group is attached to the first carbon here. For in this method we saw acid catalyzed hydration, we saw that the OH group was inserted on the second carbon. But for hydroboration oxidation, it came to the first carbon. So we can say that here in this method of preparation of alcohol from alkenes, the OH group is attached to opposite to the Markovnikov's rule. That is what to be noted in this method. So hydroboration oxidation, what we had diborane, and at the end we have hydrogen peroxide in presence of sodium hydroxide, and we get alcohol as the product and orthoboric acid. Now from carbonyl compounds by reduction of aldehydes and ketones. Aldehydes and ketones are reduced to the corresponding alcohols by addition of hydrogen in the presence of catalyst. This is known as catalytic hydrogenation. The usual catalyst is a finely divided metal such as platinum, palladium, or nickel. It's also prepared by heating aldehydes and ketones with sodium borohydride or lithium aluminum. So we can either reduce alcohols and ketones by what? Catalytic hydrogenation, by adding hydrogen presence of a catalyst, or by simply reducing with reducing agents such as lithium aluminum hydride or sodium borohydride. So if it is a if it is an aldehyde, we get a primary alcohol. So if it is a ketone, we get a secondary alcohol. Now, by reduction of carboxylic acids and esters. Carboxylic acids are reduced to primary alcohols in excellent yields by lithium aluminum hydride, a strong reducing. So, when carboxylic acids are reacted with lithium aluminum hydride, we get primary alcohol. But we know what lithium aluminum hydride is an expensive reagent. So, commercially, it's not. Carboxylic acids are not reduced in this manner. So, how do we reduce it? First, we react the carboxylic acid with what? With an alcohol to form an ester. And we do what? Catalytic hydrogenation to this ester. So, we get alcohol, and the alcohol we used to produce the ester also as the byproduct there. So this is also another method for preparation of alcohol. Now from Grignard reagent, alcohols are produced by the reaction of Grignard reagent with aldehydes and ketones. The first step of the reaction is the nucleophilic addition of Grignard reagent to the carbon to form an adduct. So here, Grignard reagent, the alcohol represents slight negative charge and magnesium has a slight positive charge. When the bond gets shifted, oxygen gets negative charge, carbon gets positive charge. And what? Nucleophilic addition is the first step in this reaction. The alkyl group gets added on to the carbon and we get an adduct as an intermediate in this process. And when we hydrolyze this adduct, we get alcohol. And the point to be noted is we get a primary alcohol only when we take the carbonyl group as formaldehyde. Only then we get a primary alcohol. In all other cases, it will be a secondary or tertiary alcohol. See here we have a secondary alcohol, and here for a ketone we have a tertiary alcohol. Now preparation of phenols first from haloarenes. Chlorobenzene is used with NaOH at 623 Kelvin and 320 atmospheric pressure. Phenol is obtained by acidification of sodium phenoxide ion. So when we react chlorobenzene with NaOH at 623 Kelvin and 300 atmosphere, we get phenoxide ion. So when we acidify this with HCl, we get what? We get phenol as the product. Now from benzene sulfonic acid, benzene is sulfonated with oleum. This oleum is H2SO7. And benzene, when we add oleum to benzene, we get what? Benzene sulfonic acid. So benzene sulfonic acid on heating with molten sodium hydroxide. On heating with molten sodium hydroxide, what we get? We get the sodium phenoxide ion. And sodium phenoxide ion, when we acidify, we get phenol. Now from benzene diazonium salts. A diazonium salt is formed by heating an aromatic primary amine with what? With NaNO2 and HCl, nitrous acid. At 278 Kelvin, diazonium salts are hydrolyzed to phenols by warming with water or by treating with diluted acid. So, when we simply hydrolyze the benzene diazonium chloride or halide, we get the corresponding, we get the phenol. So we know this process is known as what? Converting aniline into benzene diazonium chloride is called as what? Diazotization reaction. And when we simply hydrolyze it with warm water, we get it. Now from cumene. What is cumene? Isopropyl group attached to a benzene ring. That's called as cumene. It is oxidized in the presence of air. cumene hydroperoxide. So when we oxidize it, we get what? Cumene hydroperoxide. And it is converted to phenol and acetone by treating it with dilute acid. So we hydrolyze it with dilute acid and we get phenol and acetone. So we should also know that it's also an excellent method of preparation for acetone. Now physical properties. Boiling points. The boiling points of alcohols and phenols increase with increasing number of carbon atoms. As the number of carbon atoms increases, the boiling point increases. In alcohols, the boiling point decreases with increase of branching in carbon chain. So as the branching increases, boiling point decreases. The OH group in alcohols and phenols is involved in intermolecular hydrogen bonding. So we can see that alcohols and phenols are involved in intermolecular hydrogen bonding. That's also a factor for their higher boiling points than other organic compounds. Boiling points of alcohols and phenols are higher in comparison to other classes of compounds, namely hydrocarbons, ethers, haloalkanes, and haloarenes of comparable molecular mass. So here we have what? We have an alcohol, an ether, and an alkane of comparable molecular mass. And we can see the highest boiling point is for what? Is for the alcohol, second for the ether, and third for the alkane. Now solubility. Solubility of alcohols and phenols in water is due to their ability to form hydrogen bonds. So in water, they form hydrogen bonds with the water molecules. Hence, they are soluble in water. The solubility decreases with increase in size of alkyl or aryl group. So as the size of the alkyl group or aryl group increases, the solubility decreases because what? Alkyl and aryl groups are hydrophobic in nature. Now chemical reactions. Alcohols are versatile compounds. They react both as nucleophile and electrophile. So when does alcohol act as nucleophiles? When the OH bond is broken. So oxygen hydrogen bond of the hydroxyl group is broken, they act as nucleophiles. So when do they act as electrophile? When the carbon oxygen bond of the alcohol is broken, they act as electrophile. So first we will see reactions involving cleavage of oxygen hydrogen bond or when alcohols act as nucleophiles. First is acidity of alcohols and phenols. Reaction with metals. Alcohols and phenols react with active metals such as sodium, potassium, and aluminum to yield corresponding alkoxide or phenoxide and hydrogen. So we know that metals react with acids to liberate hydrogen gas. So here, when metals are treated with alcohol, they liberate hydrogen. So this shows the acidic property of alcohols. Phenols react with aqueous sodium hydroxide to form sodium phenoxides. So when they react with the base, so when alcohols or phenols react with the base, they form the corresponding salt. Here, sodium phenoxide is a salt form. So we know the acid and when an acid and a base reacts, there is corresponding salt formation. So this reaction also proves that phenol is acidic in nature. Alcohols and phenols are Bronsted acids. That is, they can donate a proton to a stronger base. So since they can donate a proton to a stronger base, they are known as what? Bronsted acids. The acidic character of alcohol is due to the polar nature of oxygen hydrogen bond. An electron releasing group such as CH3 or C2H increases the electron density on oxygen, tending to decrease the polarity of OH bond. This decreases the acid strength. For this reason, the acid strength of alcohol decrease in the following order. So, acids are what? Alcohols are acidic due to what? Due to the polar nature of OH bond. Okay, so we know in alcohol are OH. when this bond is shifted towards here, oxygen gets a slight negative charge and hydrogen gets a positive charge. Okay, so when the number of, we know that R group is an electron donating group, or it has a plus I effect. So when R group is attached, the negative charge in the oxygen atom gets further increased. As the number of R group attached to the oxygen increases, the tendency for H plus to leave is decreasing. So hence when the number of alkyl groups are increasing, the acidic character of alcohols are decreasing. So therefore, primary alcohols will have the most acidic character, tertiary alcohols will have the least acidic character. Alcohols are, however, weaker acids than water. This can be illustrated by the reaction of water with an alkoxide. So what our conjugate base of alcohol reacts with water to form a conjugate acid, the conjugate base. So the conjugate base of our alcohol reacted with water to form what? A conjugate acid. So this reaction shows that the base reacted here is a strong base. That's why it reacted with acid to form a conjugate acid. So the conjugate acid of this base is what our alcohol is. It is weaker than water here. Alcohols act as bonded bases as well. It is due to the presence of unshared electron pairs of oxygen. So alcohols are also Bronsted bases because oxygen has one pair of electrons on them, and these electrons allows them to accept protons. Acidity of phenols. The reactions of phenols with metal and sodium hydroxide indicates its acidic nature. The hydroxyl group is in phenol is directly attached to the sp2 hybridized carbon of benzene ring, which acts as an electron withdrawing group. Due to the charge distribution, phenol molecule has the big positive oxygen of OH group to be positive. So what happens here? Here in phenols, due to resonance, we can see that oxygen atom has positive charge on it. So due to this, what the hydrogen group can easily leave as H plus by shifting the bond towards oxygen. So this resonance allows phenols to act as better acids than alcohols. So we can compare the pK value. So we know that as pK value decreases, the acidic character increases. So when we compare the pK values of ethanol and phenol, you can see 10 and almost 16. So phenol is almost a million times stronger than ethanol. Now esterification reaction. Alcohols and phenols react with carboxylic acids, acid chlorides and acid anhydrides to form esters. Okay. And the thing to note here is in this reaction with acyl chloride, we use pyridine because we know pyridine is a base, so it reacts with the HCl produced here. So that the reaction will go forward. The introduction of acetyl group in alcohols or phenols is known as acetylation. Acetylation of salicylic acid produces aspirin. So it's a very important reaction. Salicylic acid when reacted with acetic anhydride, we get what? Acetyl salicylic acid. It's called as aspirin. Aspirin is what? Aspirin is used as anti-inflammatory, anticoagulant, antiplatelet. We learn about this in chemistry in everyday life chapter. Even as an antipyretic. So what's our uses of aspirin? Antipyretic, anti-inflammatory, and antiplatelet. So the action is dependent on the dose. Now reactions involving CO bond in alcohols. First reaction with hydrogen halides. So alcohol react with hydrogen halides to form what? To form alkyl halides. So ROH reacts with HX to form what? RX. Lucas test. Differential reactivity of three classes of alcohols with HCl distinguishes them from one another. Alcohols are soluble in Lucas reagent. What is Lucas reagent? Concentrated HCl plus zinc chloride. That is known as Lucas reagent. So what we should know is that tertiary alcohols. Tertiary alcohol gives immediate turbidity with Lucas reagent. Secondary also gives turbidity, but it is bit late. Primary does not. No turbidity. Does not give turbidity. That's what we should know on Lucas test. Now reaction with phosphorus trihalogens. Alcohols are converted to alkyl bromides by reaction with phosphorus trihalogen. So RH group, OH group is replaced by halogen and we get an alkyl halide. Now dehydration reaction. Alcohols undergo dehydration to form what? Alkenes on reacting with a protic acid such as H2SO4 or H3PO4 or catalysts such as zinc chloride or aluminum. So what happens? Dehydration happens. H and OH combine to form water and it escapes and we get an alkene. The relative ease of dehydration of alcohols follows the order. So tertiary alcohols are easier to dehydrate and primary are the least reactive towards this reaction. So we have the mechanism here. And we can see why tertiary reacts the most is because the process we can see there is a formation of carbocation here. So it is a slow step. So in tertiary alcohols, this carbocation will be stabilized the best. So we can see how tertiary is the most stable towards this reaction, most reactive towards this reaction. First, we have a primary alcohol ethanol. We have to give H2SO4 at 443 Kelvin and we get an alkene. For a secondary alcohol, isopropyl alcohol, we just need to give 85% H3PO4 and 440 Kelvin. But for tertiary alcohol, we just need to give 20% H3PO4 and 358 Kelvin for elimination of that. Now oxidation rate. Oxidation of alcohols involves the formation of carbon-oxygen double bond with cleavage of an OH and CH bonds. So alcohols are first oxidized to aldehyde, then to carboxylic acid. So depending on the strength of the oxidizing agent. So if we use strong oxidizing agents such as what potassium permanganate and all, we'll directly get the acid. So if we have to prepare aldehyde, we have to use milder oxidizing agents such as CrO3 or PCC, pyridinium bromobromine. So we get the corresponding aldehydes when we use these oxidizing agents. Secondary alcohols are oxidized to ketones, right? Bromic anhydride. Tertiary alcohols do not undergo oxidation reaction under strong reaction conditions such as KMNO4. Elevated temperatures with cleavages various CC carbon-carbon bonds take place. So when we react tertiary alcohols with strong oxidizing agents, what there is cleavage of carbon-carbon bond occurs and we get a mixture of carboxylic acid there. When vapors of a primary or a secondary alcohol passed over heated copper at 573 Kelvin. So what happens? Dehydrogenation takes place and aldehyde or a ketone is formed. So if we use a primary alcohol, we get an aldehyde. If we use a secondary alcohol, we get a ketone. So if we use a tertiary alcohol, what happens there? There elimination occurs and we get an alkene there. Now reactions of phenols. Electrophilic aromatic substitution. First night reaction. What we use dilute HNO3 with phenol. We get what? Ortho and para nitrophenol. So the thing to know here is that orthonitrophenol has what? Intramolecular hydrogen bonding and para-nitrophenol has intermolecular hydrogen bonding. So these two compounds are separated using what? Using steam distillation. So since para-nitrophenol has intermolecular hydrogen bonding, their boiling point is higher than orthonitrophenol. So first we can separate what? First orthonitrophenol will be separated with the steam. So when we use concentrated HNO3 instead of dilute HNO3, we get what? We get picric acid or 2,4,6 trinitrophenol. Now halogenation reacts. On reacting phenol with bromine, different reaction products. So what we when we do bromination in presence of what low polarity solids such as CHCl3 or CS2, bromine is CS2, we get what? We get para and ortho isomer there. But when we use bromine water, is similar to what? Similar to our concentrated HNO3 nitrates, we get 2,4,6 tribromo. Now Cox reaction. Phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol towards electrophilic aromatic substitution. So what happens here? Here phenol is reacted with NaOH and we get sodium phenoxide. It is reacted with CO2 in presence of an acid. We get what? We get salicylic acid. Now Reimer-Kimmel reaction. Treating phenol with chloroform in presence of sodium hydroxide. So chloroform in presence of course NaOH. We get CHO group introduced into the group, and when we hydrolyze it, we get salicylalline. The intermediate substituted benzyl chloride is hydrolyzed in presence of alkali to produce salicylalline. Okay, already discussed that. Now reaction of phenol with zinc dust. We know zinc dust is reducing in nature, so OH group is reduced. So phenol is reduced to benzene. Now oxidation of alcohol. Oxidation of phenol with chromic acid produces a conjugated diketone. So it's a very important reaction. We oxidize with Na2Cr2O7 and we get the product as benzoquinone. Now some important alcohols. What? First, methanol. Methanol is prepared by destructive distillation of wood. Okay, ethanol is also known as wood spirit. But today, most of the methanol is produced by catalytic hydrogenation of carbon monoxide at high pressure and temperature and the presence of zinc oxide, chromium oxide catalyst. So zinc oxide, chromium oxide catalyst, 200, 300 atmosphere pressure and high temperature, 573 to 673 Kelvin. We get methanol as the product. And what to know about methanol is that it is poisonous to us. Even small quantities of methanol can cause what? Blindness. Large quantities even cause death. The use of methanol is what? Which is used as a solvent in paint, varnishes, and chiefly for making formaldehyde. About ethanol. Ethanol we know from even olden times we make ethanol by fermentation of sugars or grapes in case of wine and all. And what you have to know about this is that you have to learn about two enzymes, which is invertase. Invertase does what? It converts sucrose into glucose and fructose. And another enzyme, what? Zymase. What does it do? It converts glucose and fructose into ethanol. So when fermentation is taking place by organisms, know that the action of zymase is inhibited once the percentage of alcohol forms exceeds 40 ml. So when the percentage of alcohol in the mixture reaches 14%, then zymase does not function and no more alcohol is produced there. So how do we produce alcohol that are of higher concentration? That's why we use distillation process to increase the amount of alcohol in the process. Okay, now preparation of ethers by dehydration of alcohols. So here what we have to do is H2SO4 at a higher temperature. We get dehydration there. We get an alkene. But at 430 Kelvin, we get ether there. Now Williamson synthesis. What Just 2 minutes. Okay. When alkyl halide is reacted with sodium alkoxide, we get a either that's called as Williamson synthesis. Now its properties. We already told about the boiling point, which is lower than alcohols. No chemical reactions. When we react with hydrogen halide, we get the corresponding alkyl halide. Now electrophilic substitution reaction. We have halogenation here. Bromine ethanoic acid. We get the ortho and para isomer there. In Filkov reaction, we know anhydrous aluminum chloride, presence of a alkyl halide or acyl chloride. The group is introduced at ortho and para positions. Nitration also H2SO for HNO3. We get the ortho and para nitrated products there. And what to discuss is here. We have a tertiary group on any of the side of the oxygen atom. If we react with a hydrogen iodide, what happens there? We can form, should know that iodide atom goes with the tertiary group there, and other group goes with the hydroxy group. So that's all there to know about this chapter. Hope you will understood. Thank you.